Okay, hi class. I'm seeing that people are still joining, but we can actually kick start. Uh, so again, as you can see that we took your inputs on the poll quite seriously. Thank you again for casting your votes to the poll of lectures. I think these are great topics. I actually quite agree with your taste, in picking the right directions to hear from. So today is the last lecture of the 708 graphic model class. We're going to cover another new topic on trustworthy machine learning. You will be again hearing just freshly out of the oven preparation of the slides from one of my other students, Haohan, who is working on this topic quite intensively over the past few years and has some very nice results. Just per class announcement, he will be taking over and finish the class. And then toward the end of the lecture, he will be also, maybe other TAs will join to, again, clarify or maybe to explain how we're going to carry out the project report and the review session. You will be hearing details from them and also ask detailed questions. I will try to be there, but I may not be able to make it due to another appointment. And also feel free to write to us if you have any inputs for the class so that we can do better for next year. And also if you still have concerns and questions for the class project, for the homeworks and so forth, feel free to let us know. Once again, I want to assure you that you don't need to worry about the score related issues. We will be very, very careful and positive, in evaluating your projects and your work. So with that, I will hand it to Haohan, who will be talking about the trustworthy machine learning, a very, very interesting new topic nowadays in the machine learning community. Okay, Haohan, okay. Your turn. Okay. Thank you very much.
Okay, thank you very much for the introduction. Okay, and good afternoon, class. So today, as the very last lecture of this semester, we will take a brief look into trustworthy machine learning. So as the outline of this lecture, first, I will try to convince you that trustworthy machine learning is an important research topic and is arguably one of the most important research topics nowadays. And I will show you a collection of empirical observations, and we will also briefly touch some related topics, such as the trade-off between accuracy and robustness. And then we will dive into two separate topics that are related in trustworthy, but are studied in history as two separate topics. One is the cross-domain robust models, usually studied under the name domain adaptation, and the other one is recently very popular, the adversarial robust models, and as we will see that it will introduce some results that look quite magic to human. Okay, and so let's start with the new challenges of modern machine learning. To begin with, let's say, what if I told you that we can actually predict whether you use chopsticks or not from your genome? Well, this research topic is not recommended for obvious reasons. If one actually investigates the data, they will probably find a gene called HLA-A1 that is highly associated with whether one uses chopsticks or not. However, the association between this gene and the chopstick usage behavior is only there because the gene is more frequently seen in people of East Asian origins. And similarly, in another discussion, people show that if we do not account for the nature of data properly, we may also identify some genes that account for English speaking skills, which again does not sound like something correct. Okay, these issues may also be considered within the topics of trustworthy machine learning, in the sense that we need to make sure that what is learned from the statistical models align well with the real-world scenarios, instead of some spurious signals that are only there because of the nature of data. Okay, these issues of trustworthy machine learning may date back to even further, but here I only put the reference that I'm very familiar with. And as you can see, even for the reference that I'm familiar with, is already 20 years ago. So although trustworthy machine learning is a very hot topic nowadays, it's not, it has been studied for more than decades. And here I also want to try to comment a little bit about this discrepancy, why trustworthy machine learning is valued a lot these days, while it is a topic that has been there for decades. So as we can see that it was previously discussed under these terms like population stratification and GBUS, which is using simple statistical tools to identify the genes that are associated with the traits of, for example, like some properties of human, like the disease. And back then, like 20, 30 years ago, when the community realized that these simple models can actually help the real-world biology research by identifying the candidate genes that may actually accelerate biology studies. So that we dive into the area, develop new statistical models, and soon figure out that a limitation of these models is that it may identify spurious signals. And so in my opinion, it's the real world need of this method that drive us to investigate the trustworthy of these models. But back then, well, we also have trustworthy studies of machine learning. Machine learning still mostly deal with hundreds of samples with extracted features. So it's still pretty hard if you want to apply those machine learning models in a real world scenario to actually promote someone's life. However, now deep learning has brought us into a very different era, where almost anyone with some tutorial can start to build a deep learning model, train it with a huge collection of data, and make a model and use the model to make some predictions. And these predictions in very different application scenarios are making changes to our world. So it's once again this real world need of these models drive us to investigate the trustworthiness of these models. So that is, in my opinion, one of the reasons that make trustworthy is one of the most interesting research topic nowadays. Okay. And then that's probably all about the history for this lecture. Now let's dive into the problems of this era. So deep learning has achieved very impressive empirical results in terms of accuracy nowadays, but we also see some limited, challenges of it. So one of the most prominent example is of models trustworthiness is probably this adversarial example. And I believe this figure is so popular, so probably every introduction of the related topics need to use this figure as an example. But just in case you are not sure about the story behind it, this figure is basically tells that for a well-trained neural network that can give us a reasonably high accuracy, for example, it will predict this image as a panda with roughly 60% of confidence. If we add some noise that are barely perceptible to human to that image, we can we can change the prediction of the model quite dramatically, as now for almost the same image to human, the model predicts it to be something else. Okay, and here is another example. So this example is relatively newer. So it's basically tells the story that if we combine two elements of the images, say we generate an image with the texture of an element and the shape of the cat, the prediction result is likely by the neural network will be biased towards the texture of the image, while the human mostly judge the images by its shape. Okay, and here is one more piece of empirical results that from one of our very recent observations. Let's say we first train a ResNet network and with the CFR10 dataset, and then we grab an image, put it into the model, and we generate this confidence distributions. So this is from the test set. And then we map this image into its frequency domain with Fourier transform. And we choose a radius, cut the frequency domain into the high frequency part and the low frequency part. And then with these two frequency components, we reconstruct those images. And as we can see, the image reconstructed from the low frequency components still looks similar to the original image to human. And the image reconstructed from the high frequency is basically noises. And if we put these two images back to the model, here is what happens. The model predicts the low frequency one with as something different from the original label, but the model predicts this high frequency reconstruct one still with the same label as originally. And if you are interested in seeing what's there, so here is a rescaled version of the high frequency reconstruct images. So here we can say it's basically noises, but the model is still able to recognize it. So basically the story is that the model sees the data different from us, and that is not just from one image. Out of the 10,000 CFR10 testing images, we identify a couple hundred of them. So although this story won't happen for all of the test image, but I think a couple hundred is a significant number that should raise some alarm. And now we have seen that behind. So another question is that why there are these empirical observations. Okay, we argue that one of the central problem of this modern machine learning is the misalignment of how model and how human view the data. Let's consider the scenario of the machine learning where we collect some label and data to train a model, where within the data we have some signals that we call semantic, and the remaining signals that we call superficial. Semantic signals are the one that describes how human or how the nature understands the label, how defines the label, and it is the signal that we hope the model learns. However, within the finite collection of the data, it is likely that there are some distribution-specific correlations between the semantic signals and the superficial signals. This correlation leads to the fact that there are some correlations between the superficial signals and the label. And then when a model is asked to optimize when we train the model with some data, the model basically the model is asked to optimize the loss to pick up whatever signals it can take advantage of to reduce the training error. And the model does not really differentiate these two sources of signals, leading to the fact that it will take advantage of whatever it can. And any signals that it takes from this superficial source will lead to the robustness issues that, as we will see later. Okay, so this is, we believe, the central problem, and this image will serve as a very fundamental image of our lecture today. Okay. So is there any questions so far? Okay. Okay, then with that image, let's see how we can understand the trade-off between accuracy and robustness. First of all, any discussion of the trade-off between accuracy and robustness will depend on the definition of robustness. But roughly, we can understand it from this figure here. Again, that the model will take advantage of whatever signals it can to reduce the training error. And so the reported accuracy, as we can understand intuitively, is from the both of the signals that the model picks up. However, the robust performance, although at this moment is undefined, is mostly likely to depend on this semantic signal. For example, in most literature that talks about robustness, it basically talks about that the prediction of the model will not change given small variations of the data. And the variations are usually considered small if if the perturbed data are still recognized by human, which means that it's usually considered robustness if the model aligns well with the human's recognition. And then if this source of signal is robustness, that leaves us to this source as the trade-off. For example, in the deep learning regime, it's usually much easier to capture the superficial signal than the robust signals. So therefore, if we want to collect the state-of-the-art ladder, the straightforward way will be try to exploit these signals as much as possible. That leads to the scenario that if we want to get a high accuracy, we may have to capture a lot of these signals, and then this leads to the model is naturally not that robust. Okay, and if you are interested in some formal discussions, I have collected some here, and they usually basically formalize the story we just talked about under some definitions of robustness. Okay, now we say that there is a trade-off between accuracy and robustness. And then why do we have to value the robustness when we already have accuracy? So here I want to basically try to convince you with the difference between academic and the industry. So what current academic is good at in terms of machine learning is that we usually out of the world with full of data of some tasks. When we try to do some experiment, we usually collect the data and make a partition into train and test collections, and then we build a model on the training data set, and then test it. It works well, then it's basically we can conclude that we have a model that does well. However, what the real world needs is that out of the world, we collect a data collection, we train a model on it, we show that it works well here, and we also need to show that it works well anywhere else for the same task, so that we can actually safely deploy it to the real world. Okay. And now to conclude the overview part, let's talk a very high level abstract concept about the solutions. So once again, since this is the central problem that we will deal with today, then the central solution should be inspired that, as we will see, the main problem is the fact that models pick up superficial signals. So then the main solution is that we need to cut that. Okay, and then as a very high level solution, we need to summarize machine learning at a very high level. So machine learning is basically all about generalization. And if you recall from the introduction to machine learning, this generalization, the expected risk of a hypothesis is usually bounded by the empirical risk of the hypothesis and some function of the hypothesis space, the number of samples. Okay, and usually to control the generalization, on one hand, we need to control the empirical risk. On the other hand, it's about the hypothesis space complexity and how many samples we use. As we will say later in the two separate branches of these discussions, the cross-domain robustness is all about new hypothesis space. Or in other terms, it's all about new inductive bias, or what regularization you can take advantage of. And in the field of adversarial robustness, although there are a variety of different solutions, the dominant solution, the one that works very well nowadays, is usually about increasing the number of samples. And within the lecture today, we will only talk about the solution that's following this trend, but they are the best anyway. Okay, so that's the overview part. Do I have any questions? Or any feedbacks if you guys want to. Okay. And now let's dive into the first topic, the cross-domain robustness of these models, where we will talk about domain adaptation, domain generalization, and more. Okay. Okay, first of all, let's talk about domain adaptation, and it is usually introduced as this sentence that it studies the problem that model is trained on one distribution or domain but tested on another one, and usually this another distribution or domain is characterized by the term that is similar but different. And the majority of the work is about the empirical studies, so we didn't really actually define this similar but different, but I hope it should be understood pretty intuitively. And then within the umbrella of domain adaptation, we mainly have two different categories. One is the supervised domain adaptation that it studies the problem that the labeled samples in the test distribution are also available during training. And for example, if we want to build a dog versus cat classifiers, we from those photos, and we try to adapt the model into the sketch results and try to make sure try to evaluate whether this model actually understands the concept of dog and cats, for example. And then the supervised domain adaptation usually follows the setup that we have these collections of photos from dogs and cats, and we also have a small collection of these sketched dog and cats. And then we have this probably very as a very natural follow-up, this unsupervised domain adaptation, where only unlabeled samples in the test distribution are available during training. And this is actually, I think when we talk about domain adaptation, this is more than often the scenario that we talk about. So usually nowadays, most domain adaptation works are talking about unsupervised domain adaptation, especially in the computer vision area. Okay, and since now we have seen that the problem is updated to some new regime where we have the discrepancies of these distributions. So the generalization behavior of these models may have changed. So to start with, let's say that how is the generalization changed in this domain adaptation scenario? And first, since now we have two distributions, and for example, very intuitively, we can say that in the example at the previous slide, we can say that if we want to build a classifier on photos about dogs versus cats, and we want to generalize it to sketches, it's quite intuitive that the model, if it really learns the concept, it can do well, right? So in some sense, the distributions between photos and sketches are still near each other. But that may not always be true. For example, what if we want to build a model on the dogs and cats on Earth, and then try to generalize to some alien world where maybe all those animals have 6 legs. So to begin with, that we need to have a good measure of the divergence of 2 distributions. Here we introduce this H divergence. It's a measure of 2 distributions given a hypothesis class. And it depends on, we need to introduce this term IH first. It's the set of those hypotheses that are characteristic functions for the domain, which means that for any sample that the hypothesis returns 1 if it comes from the same domain, comes from the domain of interest. And then H divergence is mathematically defined as the following, where is the supreme hypothesis out of this hypothesis class, where we have the maximum differences of the samples under these characteristic functions. So this may raise some confusion, but we can intuitively understand as the H divergence is the maximized differences that a hypothesis within the hypothesis space can identify. Or to help understand this term, let's say that if our hypothesis class is highly restricted, that all the hypotheses are returning some constant given data, then this divergence will be 0, since they will always return the same thing. So within a very limited hypothesis class, we cannot really differentiate these 2 distributions. Let's say if the hypothesis is highly expressive, then it should do well in describing these 2 distributions, then this divergence term can be large. But even the hypothesis space is large, if these 2 distributions are, for example, identical, then the result is still a small term. And collecting those scenarios discussed above, we can say that this divergence is a property of both the hypothesis space as well as the source and target distributions. Okay, and here is the description over these 2 distributions, and then they also show that it can be estimated from finite samples with this bound, where this is the divergence of the collected samples of these 2 distributions. It found the divergence with some concentration terms. And then this divergence from finite samples can be estimated with a domain classifier. And I hope this looks familiar to most of us. Although this work is introduced in 2010, and but nowadays, because of the popularity of GAN, this kind of thing should be quite familiar to us. So it's basically says that to estimate the divergence of 2 distribution empirically, we can simply build a classifier and ask the classifier to classify those samples from 2 domains. Okay. And then with these results, and together with a little bit more technical terms, we can get this very popular generalization bound of domain adaptation. So it's from this paper in 2010. It basically says, for the equation here, it basically says that the expected risk of the target distribution is bounded by the expected risk from the source distribution, together with this divergence term of these 2 distributions, and this lambda, where this lambda means that the error of the optimal hypothesis on both source and target distributions. And one may need to notice that this is also the expected risk, so different from the most of the generalization bound that we see. But however, it should be fairly simple to rewrite this with the empirical risk together with another concentration terms. Okay, so then basically this terms tells us what we need to do if we want to get a small error on the target domains. And here, this divergence talks about that we need to have a hypothesis space that is not small enough so that the model does not differentiate the source and the target distributions. And then these two terms tell us that we need to have a hypothesis space that is large enough so that we can actually find the hypothesis that gave us a small error. Okay. And with that background, let's look at the first method we will talk today. It's called domain adversarial neural network. It's probably one of the most popular domain adaptation method in this deep learning era. And to get a good understanding it, let's first put this equation here. So it's all about it's all about that we need to find a hypothesis that cannot differentiate these two distributions while it have both small errors. So the idea is built on the fact that we need to train a classifier that has small error on the source distribution, while it is unable to differentiate the source and target distributions. And then back then they introduced this idea called domain adversarial neural network. It's basically a standard neural network structure with this green one and blue one. Together with a new component is this domain classifier, where we consider these blue ones as feature extractors or some component that's to learn some embeddings. And then this domain classifier is built upon these features or embeddings that is used to classify whether those images are from source distribution or target distribution. And meanwhile, this class label, this actual predictors or the actual classifiers is used to make the prediction based on these embeddings. So back then they introduced this gradient reversal layer, but nowadays I think again due to the popularity of GAN, we can understand this as the adversarial gain. So basically, the domain classifier is optimized to do as well as possible in terms of classifying this domain information, while this classifier is optimized to do as well as possible in terms of making predictions, while this feature extractors is optimized to help this classifier as much as possible, meanwhile to fool these domain classifiers as much as possible. Therefore, as a result of this method, the representations learned in these middle layers will be very representative for label classification and will be very uninformative for the domain classifiers. Okay. Is there any questions so far? Are you guys still with me? Or did I went too fast or slow or something? Okay. Okay. Actually, hope you. Okay. Why do we want the model to be unable to differentiate the two distributions? So this is a direct result from our bound in the previous slide. Oh, sorry. Where the generalization behavior from the where the generalization error on the targeted distribution is bound by the model's ability to differentiate these two distributions. So one thing that is good is that this is from mathematical result. On the other hand, we can also try to understand this intuitively. For example, if we can really learn a good classifier, for example, in the dog versus cat example, that's the model that actually learns the concept of dog and cat should be applied to multiple distributions like the photos, the sketches, or whatever other image qualities. If so, if they understand the if the model actually understand uh, if they actually understand the concept of cat versus dog, then the model should be invariant to the distributions. Okay, so I hope this intuitive answer helps. Does this bound also work for supervised domain adaptation? I believe so, since supervised domain adaptation is maybe it's a subset of the unsupervised is a subset of the supervised. You all need to do is just ignore the labels, right? You still get here, but probably with supervised domain adaptation, you can get a tighter bound. Okay. Actually, hope that we can have some questions here. For example, as we see in the last slide, the bound actually depends on the small error on both source distribution and the target distribution. And now, despite that, this method is probably the most popular method in the field about this topic. People argue that this gives some sort of a misleading message. For example, in this paper, uh, uh, they argue that the invariant representation and small source error, small source risk, which are the stuff that the domain adversarial neural network promotes. These two elements are not sufficient for a good domain adaptation method. For example, they showed this example where they have these two different domains, and we can in this example, we can say that there exists an optimal classifier. Let's see here that it can differentiate these two labels. But if we push for the invariance, we will say that once the model cannot differentiate these two domains, we cannot find a simple and good classifier anymore. So again, following the original bound, it should be the small risk on both source and the target distribution, but it's probably too hard to optimize on the target distribution. And within this work, they argue that the labeling function also matters. So the bound should include this term. And to understand that intuitively, let's say that now with our classifier of dog versus cat, we try to adapt it to the alien world where all the animals have 6 legs. And if we do not want to differentiate them, then basically all we need to do is ignoring those legs of these animals. Then the model should also do well. But however, that aliens may not call their dogs dog or cat's cat. They can basically reverse it, and then our classifier will face a very significant failure. And so that's some intuitive translation of this work. And despite this, domain adversarial neural network is arguable in terms of this performance. It has been considered as one of the most popular methods for domain adaptation in this deep learning era. And also it has inspired tons of follow-up works. And most of these works are following the very high-level concept of that DNN, and it's essentially about to design an inductive bias that learns an invariance representation between source and the target distributions. So basically, if we want to design a new and powerful domain adaptive neural networks, the first question we need to consider is that how do we force the representations to be invariant? And so I actually want to try this question to the class. Can anyone try to give some methods that can help to force the invariance of representations. I think we should have seen quite a few methods. For example, at least we say that we can use an adversarial classifier on the top of these representations, and then very intuitively we can design some distance metric and try to regularize the distance. Okay, and so there is first of all, there is probably a huge collection at the very beginning stage. There is a huge collection of this method that try to regularize this distance metric to force the invariance. And then people try to design these adversarial classifiers to lead to the invariance. And there are also some other strengths. For example, they built the model to reconstruct those images from source and target distribution, and hope that a successful reconstruction can lead to the a good learning of the invariance. So basically, in my opinion, that domain adaptation is mostly all about learning an invariance representation. So for how many methods we have to introduce invariance, we probably have how many methods to for domain adaptation. And so here I only introduced 3 of them, but it should be good enough for you to understand the most works out there. Okay. And here, other than that, I also want to discuss about one method that is quite new. As you can see, it's from 2020. They different from the previous trend that they didn't really take a significant advantage of the inductive bias, but they try to take advantage of the model of samples. Or in other words, they try to do the domain adaptation with the help of other unlabeled samples. So they introduced this idea as self-training for gradual domain adaptation, where the self-training is about this concept that with a is a semi-supervised learning term. So first of all, with some labeled samples, we can train a classifier, and then with that classifier, we can use the classifier to predict those unlabeled samples. And then together with these unlabeled samples, we can update a new model. So they demonstrate that with this data set, where we have these photos from early 20th century to late 20th century, where the actual appearance of this human probably changed a lot. So if we want to build a classifier on this very beginning stage and directly apply it or adapt it to the late stage, we may get some unexpected results. And then their method is about gradually use self-training to update models with these intermediate distributions. For example, this figure is from their paper. It describes that the how this gradual self-training mechanism can help. For example, we have these labels. We have these samples that are labeled with green dots and red dots. And if our final distribution is here, directly adapt them here will probably lead to some very bad results. And then we can assume that the distribution that near this original one is somehow in some sense similar to the original distribution. So we can basically perform this self-training gradually, and as you can see that the update makes more intuitive sense. And this is mostly a theoretical paper. Self-training is not invented by them, but they offer some good understanding about the behavior. And together they also offer some practical insights. To summarize that, it says there must be some incentive for the model to update itself. And for the incentive, they argue that regularization is necessary. And also this term called label sharpening is necessary. And the label sharpening means that although this model makes a probabilistic prediction, for example, this figure may be a good illustration that we have this light blue. It's like the model considered this dot to be blue, but not with that high confidence. And if you have this, the model may not actually update itself. So you have to actually turn this to be fixed 0 and 1. Okay. And that concludes the domain adaptation part. And okay, we may have to go a little bit faster. So then we have this question that are models trained with domain adaptation good enough for general real-world deployment? So the answer is probably no. Otherwise, I won't put this term here. But why exactly? And I hope this is also intuitive enough. That's because there might be other distributions that are not considered as the target distribution during training, and that is not what we want. So to account for that problem, we introduced this, there is this field called domain generalization, where it basically talks about that we can train a model with samples from different domains and then test with a new distribution. Therefore, a good test accuracy may indicate that the model actually learns that concept and can be applied to hopefully any other distributions that close enough. And here is an illustration of the idea. So now we have the different collections like the photos, the cartoons, the paintings, and then we train the model and apply it to the sketches. Okay. And oh, by the way, recently there is a paper that somehow got a good popularity called Invariance Regularization, Invariance Risk Minimizers. And it essentially talks about this domain generalization idea that has been there for 15 years. And then over the last 15 years, or mostly probably only in the deep learning era, that here are some highlights of those methods about domain generalization in deep learning era. And since now we don't have any information on the targeted distribution, we need to take advantage of what we have, which are the domain identifications. And then the central assumption is that the model that can generalize similarly and well enough across different training distributions is likely to generalize well to an arbitrary targeted distribution empirically. And for the method development part, the first is again forcing some sort of invariance across different distributions. And for any method we have seen in the domain adaptation regime, we can probably borrow it and apply it here. And then here I collect some pretty unique methods that cannot be applied to the domain adaptation field. The first one is this: we can build some ensemble of classifiers, one for each domain. And another one I think is a quite clever idea that we can apply the meta learning. For example, during training phase, we can iteratively split those training domains into a virtual training and virtual testing one, and then build classifier upon it. Okay, and here is a brief introduction for domain generalization. Again, it's mostly about invariance. So I hope that as long as you really understand the fact that this invariance can help in generalization and at least intuitively, then in the future when you see these similar papers, or in the future when you have the need to develop your own methods to publish a paper, for example, it should be fairly easy for you to catch up a majority of this field. Okay, and then let's ask this question again. Are models trained with domain generalization good enough for a general real-world deployment? Again, since I put this here, you probably expect no, and then why not? We argue that the partitions of domain may not always be available in the real world. For example, during the introduction of deep learning, introduction to machine learning courses, or we probably have all asked and answered that question, that when we say a clustering result, when we say a clustering method, or when we say a data collection and we are asked to do some clustering work, then the first question is that what's the number of clusters we expect? So I think that's a good example for the real world, that to show that the difficulty to understand the partitions of domains in the real world. When we have a collection of data, we barely understand that how many distributions this data come from, let alone to answer the question that which sample comes from which distribution. So now this new problem started the problem that we trained the model with a collection of samples that may come from different domains, but we don't really know, and then tested with a brand new distribution. Here the difference is that in the training we do not have the clear partition of these samples, and we argue that this is probably a problem that is real enough. And then how do we solve it? So now we don't have any extra information that we can borrow. Okay. Then this leads to the very central problem that we have discussed today. So essentially it's about how do we control the model's ability in capturing the superficial signals. And so it leads to the fact that the solution that we need to find a hypothesis space that pick less superficial signals. And here, since this scenario is actually advocated by me, here I plan to introduce like two of my previous results that as some case studies or as some examples to show that how we can get a better performance in terms of the cross-domain generalization when we control this. But probably I will only have time for one of them. So let's skip one. So the first one is about how do we build the inductive bias to make sure the model does not learn those texture of data. And then the second one is about the we build some inductive bias and regularization to make sure that to push the model learn some global representation of the data. So here we want to say that the challenge is that the neural network can predict through some local signals that do not align well with the annotation of the data set. For example, if we want to build a classifier of turtle versus tortoise, and we first collect the data from a simple Google search of those images, then these are the results returned by Google, as we can see that all the background of those turtles are blue and the background of those tortoises are likely to be green. So when we build a classifier, the classifier probably have a very high performance and it should be built quite easily, since all it needs to do is to look at the background to find the blue. Okay, but that's despite that it can have a high accuracy, that's not what we want, right? We want the model to actually understand the concept. So to do that, we introduce this patch-wise adversarial regularizations, where we start with a simple neural network, a convolutional neural network, where the first convolution layers, for example, has this C channels, and then it has this M by N patches, and each of them summarize area or a local patch of those images. And we want to make sure that they do not summarize the representation that are predictive. So to do that, for each of the patch that have C channels that we consider that there are this representation from these C channels are the C features, and then we build a simple C by L classifier, where L is the final labels. In our case, L is 2 as C turtle versus tortoise. And then we built this classifier to take advantage of these features and to make a prediction. Since we have n by n patches, the final output will be n by n predictions. And then borrowing the idea of adversarial training or basically the adversarial game, we can push these representations to be unable to make predictions. And so the top layers are forced to learn some global concept of the model. And together with this work, to help evaluate this cross-domain generalization, we introduced probably the largest domain adaptation dataset so far. We introduced a new copy of ImageNet test dataset, where it has 50K images, 50 images for each of the 1,000 ImageNet classes. And then the idea that we should, if the model really learns the semantic concept of the data, then it should understand the concept well and should generalize well directly to these sketches. And here are some examples. And the third one is my favorite. As we can say that with the regularization, our model can understand that this is a dog, where the original model thinks this is a mob. And the fur of this dog actually looks like a mob to some extent, right? And also keep in mind that this is a 1,000 classification, so all these confidence are fairly high. Okay, that's our discussions of cross-domain robustness. Do I have any questions? And if not, we will start the adversarial part, and which I guess is can accept your guess more. Okay. Okay, now let's start a new journey about adversarial robustness. So first, we need to answer the question that what are adversarial examples, and we can recap very briefly with this very popular example. So adversarial examples are basically samples with very carefully crafted patterns that are added to the original sample. And then those new samples look identical to the original one to human, but it's predicted by the model significantly different from the original samples. Okay. And this sounds actually quite magic, but probably not rigorous enough. So let's get it rigorous. So with the sample X and the model theta, the adversarial example X prime is a result of an optimization problem where we want to optimize the distance between this new sample and the original sample, where we want to make sure that the prediction of this new sample is different from the original samples. So I hope this does not sound too magic anymore, since it should be a well-defined mathematical problem. But again, how magic it looks to human depends on the choice of this distance metric. For example, in most of those popular examples, this D is an LP norm distance, where human can hardly differentiate the differences. But if we consider this D as some rotation, the adversarial example is probably not that popular, probably not that magic. Okay, and also to make this more rigorous, this is a general formula, but in practice, we also need to add another constraint that we need to make sure this newly generated sample is a valid sample. For example, in the image area, that this new samples must have the pixel values ranging from 0 to 255, or from 0 to 1 depends on your income, but the input, but it must be an image. Okay. And now we answer the question that what are adversarial examples. Then the other question is why there are adversarial examples. And since we have discussed so far, I hope this is expected. So adversarial examples are direct outcomes of the fact that models are capturing superficial signals. This took a while for us to get there, but nowadays this should be quite fairly straightforward. Okay. And why is adversarial robustness such a popular topic? Well, I think to begin with, we need to acknowledge the fact that variance might actually be that it appears magic. And the other one is the thing that we have iteratively emphasized in this lecture, that the alignment between human and model may play a significant role in the real-world deployment of machine learning. Okay, and due to its popularity, tons of efforts made to defend a model against those adversarial examples. But unfortunately, even more efforts are made to generate new adversarial examples. For example, okay. So here I collect a set of attack versus defense methods that are nowadays are still relevant. And we have a huge collections methods back then, and probably many of them are worth a detailed discussion. But here, due to the time limit, I will only introduce two attack methods that and two defense methods. Okay. The first one is this fast gradient descent method. FGSM is probably one of the earliest method, and I think they are still relevant today due to its simplicity. And before offering the actual mathematical definition, I want to introduce an intuitive understanding of the method. So intuitively, I think this method is basically a reverse way of training. During training for one epoch, our goal is to update the parameters to decrease the loss according to the gradient. And then FGSM is the reverse way, is to update the data to increase the loss according to the sign of the gradient. And to formalize it, it will look like this. So basically, this new sample will be a perturbation of the original sample, depend on the step size and the sign of the gradient with respect to the sample. And of course, to make it valid, we need a constraint that to make sure it's still a valid data point. And this popular example is actually generated by FGSM. Okay, as you can see, the difference are barely perceivable to human. And then the other very popular method is this PGD, which stands for Projected Gradient Descent Attack. And a little bit fun fact, it's actually previously invented under the name BIM, as also as an adversarial attack method, but it was made very popular in this magic paper, and probably because they demonstrate that PGD is one of the most powerful attack methods. And the algorithm is also fairly simple. It's basically performing FGSM multiple times with smaller step size. So to give more details, the algorithm is that we start with a random permutation within the LP norm ball. For example, here we consider this L2 ball, and this is the original samples. And then we start from a random perturbation, for example, here. And then we perform FGSM iteratively for every step. We calculate the gradient, the sign of the gradient, then update the new sample a little bit. And we repeat this for multiple iterations. And while these two examples are pretty nice, but in reality, we may say that these examples sometimes get out of this ball. Then we simply project it back to this boundary. Okay. So despite its simplicity, it's probably the most powerful attack method nowadays, if we are talking about the LP norm distance. Okay. And then with these attack methods, we want to introduce two highlights about the defense methods. And the first one is from our lab. It takes advantage of the worst case example. If you still remember from the overview slides that the domain adaptation works usually takes advantage of the hypothesis space, while this adversarial defense method usually take advantage of the samples. The most successful methods usually take advantage of the samples. So since we need to take advantage of the worst case sample, we need to first identify it. And with the collection of attack methods, it should be fairly simple. And then this trace defense method is essentially about a regularization. We need to regularize the distance of embedding between this original sample and the new perturbed samples. So in this paper, the actual implementation is the KL divergence regularization over the softmax. But since we have talked about several invariance regularization, it should be straightforward that there are different other different formats of the same method. And for example, if you regularize the L2 distance of logics, then you lead to another method called adversarial logic pairing, which is also a popular method. And here is a brief illustration of the effectiveness of this method. So where these dots are the actual sample and these squares are the LP ball around these samples that the adversarial examples are allowed. And this is vanilla training, and as we can see that we don't really have the control of the decision bound. And this is the training with this trace idea, and I think it should be very intuitive that we expect the bound to enclose this adversarial ball. Okay. And this method enters the NeuralNIPS 2018 competition and won the first place out of 2,000 submissions, surpassing the runner-up with more than 11%. Okay. So just a brief summary of the performance. Then that method is already pretty good, and here is even more popular one. It's basically adversarial training as a defense, and it also comes from this metric paper. And to summarize the idea in one sentence, it's essentially about augment the training data with generated adversarial examples during training. So it is indeed as simple as it is, but it's very powerful. It's probably the most popular defense method when it is integrated with PGD, which is the most powerful attack method. And it also has very impressive empirical performance, and it's also fairly simple. So we will see very soon about its impressive empirical performance. And for the simplicity part, I don't have it within this deck of slides, but we are not happy with its simplicity, and the community is trying to make it even easier. So for example, faster method, faster than PGD, way to generate these adversarial examples will be very relevant. And there are a couple of papers that if you are interested, you probably can take a look after the class. Okay, now let's go back to look at the empirical performance. So here is from this paper. They talk about that when we train a model with adversarial training and PGD, the adversarial examples are not that magic anymore. So the model is fairly robust at this moment. For example, if we get a model that is, for example, if we train a model with adversarial training and PGD, then with these three samples, and we perform the targeted attack to on these three samples. And I think these attacks do not terminate when the images are good enough to deceive the original model, but to try to maximize the likelihood. So here we can say that it can actually show the patterns that align at least better than the previous examples align with human. Okay, and yeah. And another very interesting point, I think, is that the model can automatically identify that which part of the image that is likely to turn into another label. For example, they find that it probably makes more sense to turn this part of the crab, or is this fish or something, into a dog. And for different labels, they may choose to perturb different components. Okay. And also within that figure, they show that the adversarial training with PGD can work pretty well in multiple different tasks. For example, the same model may able to fulfill these tasks such as the generation in painting, super resolution, and these ones. And the results, the advertised results from this figure is very good. But I think in their paper, they also acknowledge that if you look at this, if you pick a random image that they do not look this good, but it's also reasonably good. And also since this is about the idea that once the model can align well, reasonably well enough with human, then the model can automatically perform multiple tasks. I think the result is still significant enough. Also, but on the other hand, these results probably may not work as well as the single models that are specifically trained for one of these tasks. Okay, so this is about the power of this adversarial training with PGD idea. And then with this impressive performance of adversarial training with PGD, can we conclude the development of this defense methods? No. And it's simple, but probably not simple enough, as we have seen previously. And another more important reason is that there might be other attack methods that is simply not invented yet that can penetrate the defined model. Okay, and so does this mean that this research area is endless? Well, fortunately, the community moves to provable robust models nowadays. So basically, if nowadays, if you want to invent a defense method that actually shows that our model is robust to some attacks, the community probably will not value this method as much as they did previously. So nowadays, if you want to promote your own defense method, you probably have to show that mathematically it will not be penetrated by any methods within the constraint of adversarial attacks. Okay, and just to show this a little bit example of probably defense method here, I only include one example. It's called this certified robustness through randomized smoothing. And I choose it mainly because it's simple and intuitive, and as a probable defense method, it probably involves the least amount of math. And the idea is simple. It basically says that for a model FX, we generate another model whose output is the majority prediction of X when it is perturbed with a collection of noise. Probably this image is a good illustration that for X whose prediction is blue, that we want to generate this G by perturb and sample all these perturbed examples of X around this centroid, and then the final prediction of this G will be a voted result of this prediction. And so I think this idea is not invented by them, but they are the first one to show that this method can offer certified robustness, which means that within their method, within the L2 norm distance, the model cannot be penetrated with any other existing L2 distance attack method. Okay, and with that conclude the adversarial robust discussion, which a little bit hasty, but I hope it's fine. And so looking into the future, I think again, it's all about this figure that we need to control what the model picks up, that once the model actually picks up the semantic information, that we can safely say that the model is robust enough. Okay. So it's roughly the time that we need to conclude this lecture. And so here we talked about the new challenges of machine learning, and we talked a little bit more about cross-domain robustness, cross-domain robust models, because it has, I think, more than 20 years of history. And also for a new topic that is adversarial robust models, since it only have like a history of maybe 8 years, 5 years. So we spend a relatively shorter time on it. Okay, do we have any questions in general? If no, then maybe I can conclude this lecture. And also, since this is the very last lecture we have in this semester, I just on behalf of the PGM teaching teams, just want to thank you guys to be with us for this semester, and I hope you guys have a very good time and in learning these new technologies. And I hope we have done a reasonably good job, and also thank you guys for being understanding when we made some mistakes. And yeah, and also we thank John for supporting us in this Zoom technical, in the technical issues of Zoom, and also, yeah, good luck in general, and in the future, good luck to your homework, and good luck to the projects, and in general, good luck to your academic performance. And if you are interested in this in this trustworthy machine learning, and you want to involve in the research or something, and feel free to contact me if you want. And also, maybe stay healthy and stay at home. Let's fight this COVID-19 together. So that's probably it. If you guys want, I think the information on Piazza already. So the deadline of both homework 4 and the project, and both the submissions in terms of report and the final presentation will be May 6th. I think it's roughly that time. Please double check on Piazza. And also the submission of the final projects will be including a report as well as 10-minute pre-recorded videos. And please make sure that your members of the team evenly split the time, and also make sure that your face show up during the presentation. Do we have other questions? Then if not, then that's all. Thank you.